All right. It's been a while since I hopped on and did a stream. Um, Figured I'd start doing a stream for this new book and course that I've been working on. The course is a parallel computing course. So let me launch my browser here. Actually, you know what? Let me do that. And I think I have it. Winlog? Yeah, this guy here. So I've been working on this parallel computing course, which is Stanford Kayvon. This dude here. So the last, I think they do it every fall at Stanford, but the last session was 2025. The recorded videos are from 2023. So the videos are more dated than the slides on the lectures. But one of the things that he recommended in the syllabus here, yeah, here we go. Lectures reading, maybe? No. Home? Where is it here? Course info, maybe? Book. Textbook, here we go. There's no required textbook, however, you may find the following textbook helpful for architectural topics. However, generally these days, there's plenty of great parallel program resources available free on the web. I wish you had provided those, to be honest, because it leaves less to the imagination, but I guess he's saying, you know, this is graduate level. I think this is a graduate course. It might be an undergrad. But he's saying, like, you're operating at a higher level, you should be able to find these resources yourself. Makes you think, like, what am I paying to go to Stanford for? But it is what it is. I'm sure he's not getting compensated very well for his incredible work on preparing this course. So I'm not going to criticize him too much, but it would have been nice if he provided some of those resources here. Anyways, he does recommend what is referred to as H&P, Hennessy and Patterson, Computer Architecture. He recommends 6th edition, but even at the time this course is given, I think might have been around the same time. But the 7th edition came out. Computer Architecture Quantitative Approach 2025. So it's very up to date compared to most computer architecture books that I've encountered, which are quite old. So I picked up the physical book, and then I also downloaded the textbook in a PDF format. I bought the physical book, and then I decided I'm going to buy the ebook as well. So it cost me a lot. But the reason why I decided to get the ebook is, well, first, so I can like read it on stream. I can also copy text and stuff out of here if there's any code examples. Actually, you know what? That doesn't work very well here. Let's just say it's easier for me to get data out of this PDF by print screening and doing OCR or whatever I have to do. It seems like selecting doesn't work, unfortunately. Maybe that's like a annoyance they put in here to prevent people from copying, like a DRM type thing. That's kind of silly. Wish they wouldn't do that. Anyways, it's easier for me to copy stuff, like if there's code examples. I don't think there's a lot of, this is a very code heavy book, but if there's any type of data or code that I want to like copy and, you know, run in a program or something like that, it's easier for me to do that. It's also easier for me to talk about stuff on the stream, having an ebook versus the physical book. And then the third reason is the physical book, buyer beware, it is black and white. It's a very expensive book. It's about $90 depending on where you get it. I've seen it range from like 85 to like 100 and something. So it's a pretty pricey textbook. And unfortunately, while the paperback here has a really nice cover that's in color, all the content is in black and white. So that was the third reason why I decided to get the PDF, is to be able to see the diagrams in full color. Because there are some things in here that I think it helps to have color, like this, you know. I mean, you can tell from the lines here which one's which, but you get the idea. There's stuff in here that's in color, that it's like these die shots. If I disable the night mode, it's just nicer to have like a color die shot instead of looking at black and white. So yeah, I started reading this off stream. I got to page 15, so I didn't get very far. My current plan is to just read it casually as a supplement to this course. And then one of my buddies I'm gonna be reading it with, we decided to read it together because he was interested in it apparently. It was just surprising because I didn't think he would be interested in it, but it came recommended by a AWS Distinguished Engineer, and I think he respects that guy enough to dive into his recommendation here. So what we're going to do is we're going to read the first chapter, and then I told him we would decide on what topics we want to dive into, because this is really a book. While I'm comfortable reading it cover to cover, I know that he's a family man. He doesn't really have the time to read it cover to cover. So I think that's going to be my approach to this book is reading it casually, with my buddy on a schedule that he defines, and then also diving into specific sections where it's applicable for the parallel computing course that I'm working on. So yeah, that's where I'm at. And so I read 15 pages already, just in bed the other day, and I realized that so this is a textbook that's like later undergrad or graduate, and I've heard a lot of people talk about their master's thesis and how they were reading it for their master's, so graduate level courses and graduate level work. So I think this is more of a graduate level textbook, and in reading it, I have no problem reading it. But as I was reading, I was like, oh, these authors kind of make a lot of assumptions about your competency with the subject matter. Even in the first chapter, which is surprising, because usually the introductory chapters are really like easy on-ramp into the material. They just kind of start throwing all this terminology and stuff at you. And that can be super intimidating if you're like an undergrad and you don't really have that background yet. Just background knowledge and experience. So what I'm thinking about doing is developing some short videos that kind of explain some of the topics in the book as kind of like helpers to get people familiar with those concepts if they haven't encountered them already, if that makes sense. Basically, I want to do videos that are targeted to my buddy because I know his background, and while he's a very well experienced programmer engineer, I don't think he's operated at this level of computation before. So one of the things that popped up here that I saw that got me thinking about this was this table here. So I'm not familiar with RISC-V or even ARM for that matter that much. I have a tiny little bit of experience with ARM, and I have an ARM machine that I do run ARM code on occasionally. But all of my instruction, like machine level programming, assembly programming stuff, has been with x86-64. I've read the CSAPP book, which is all AMD 64, and I've read a previous, about 2017, I think, somewhere around there. I read a short book on AMD 64, and I have a couple other books that I'm kind of casually like looking at examples in that are all AMD 64. I spent the machine I'm running on right now is AMD 64. I spent most of my time dealing with AMD 64 on the server. So yeah, I guess even with my emphasis on AMD 64, I can still look at this and kind of understand what's going on. I know the difference between caller and callee registers. I know, what stack pointer is, thread pointer. I know what function argument registers are for. I haven't encountered this constant value register. That's a new one to me. I guess my guess as to why you would have a constant value register of 0 is so that you don't have to encode the immediate value in the instruction. Like if you're initializing memory or something, or initializing a value or a register, and you want to just assign 0 to it, I think in AMD 64 you have to encode the value as an immediate value. In fact, I know that you have to do that. It's either you're coding it in the instruction, or it's in memory somewhere, or it's in a register. So if you want to have a hard-coded value, you can write that hard-coded value to memory, and then read from it and write to your registers or wherever. I guess it would just be your registers in that case. Or you can have an immediate value. And so because AMD 64, or because Arch 64 ARM reduced instruction set architectures have a fixed width instruction, so the byte length of the instruction is fixed, that means that it's harder to encode immediate values in those instructions. That's I guess. It's complete guess, but that would make sense on some level why they would do that. So, given my background and my context, I can kind of like walk through this table and kind of like reason about it. But I know this guy sitting down, he's going to sit down and like, he's not really going to know the difference between calling and caller saved registers and calling conventions. And he's not going to know, what instruction set architectures are. He's not going to really know about registers in general. And so I kind of want to create some content, for lack of a better word, for my YouTube channel, where I go through and I just present these ideas and explain them from a very minimal computer science background, if any at all. Just someone who's like freshman computer science should be able to understand these videos. So yeah, that's kind of what's on my mind with this book. And yeah, I guess, I was just wasting time this afternoon. I was like, let's just hop on and like get started on some of this stuff, maybe do some reading, or maybe actually make progress on this course. Because I watched 2 lectures, but I haven't made any progress on the coursework. I don't know. I think I have a little bit of anxiety around the coursework right now. It's funny, like I shouldn't have anxiety around this coursework. It's just, I don't know. It's something about getting started. I think that's always my problem. Like sometimes getting started on something is super easy. Like you just fall into it and it's great and you make lots of progress. But sometimes getting started is just really hard psychologically. And inevitably, once I get started on something, I find that getting started was the hardest part. That everything kind of flows naturally. I'd say 99.999% of the time, I'm worried about working on something. It's the worry that's really the blocker, the psychological barrier. And then once I get started, it's like, oh, this isn't that bad. Like, what do I fear about working on it? On this coursework? Failure. I guess there's a fear of failure. There's a fear of the difficulty. That's one thing that I guess I'm dealing with right now, is the fear of the difficulty of the material. And then ironically, there's like a fear in my head of not starting, and that prevents me from starting. Isn't that crazy? So let's just like take some breaths here. Deep breaths. I find deep breaths always helpful. And then let's just start small. So I'm going to close out a textbook and I'm going to go back over to the course. Actually, I think it was over here. Yeah, assignment 1. And we'll jump over here. I think I put it under, where's that at? Here. Okay. Don't know what happened here. Interesting. So I am on master of the master branch. I could see me modifying these things, but what are these? Oh, these are build products. I did add the cling D. I did not add any of this stuff, so needs to be get ignored. These are outputs from the compiler, this ISPC compiler. So prog1 Mandelbrot threads, get status in here, and we're gonna say git add main Mandelbrot thread, and git add.clingd, get status, and then we're gonna get ignore all this stuff. Vim dot get ignore Mandelbrot. Basically, I'm just gonna copy all these except for the ones in the directory. And can I just do foreground? No. Let's go back here, paste them in there, delete that, and do that. Don't need that one. Oops. And then I wonder what this ppm thing is. Okay. Oh, those are actual images. That makes sense. Okay. Get status. Get add dot get ignore. Okay, so that gets us back to a clean-ish working directory. Let's go to prog3. This is where I was testing out ISPC. So I think I just do make clean on this directory. Hopefully, get status. So this also, if you look at what make clean does, it deletes the objects directory, ppm files, any tilde files. I don't know why you would have those, and then the named build targets here. So we should just do the same thing where we have our get ignore there. But I will leave that for a future time when I'm working on that part of the assignment. Okay, so let's go back to under prog1. Sorry, prog1 threads. And then if I recall correctly, so we had these two ppm files, and if I open Mandelbrot serial ppm, it came up black, but I think I needed to open this with a different program. View ppm on Arch, yeah. This is convert, but I think there was fe. Was it fe? No, it wasn't fe. Display, that's what it was. Display Mandelbrot serial. So you can see Mandelbrot serial is working. And then if we do Mandelbrot thread, does not work. So we need to modify our Mandelbrot thread CPP to fix that, and that's where I left off here. So here I think we're just going to call the same. Interesting. This is calling threads. We're going to call Mandelbrot serial on everything. Okay. Since it's void, we don't have to return anything. And then these worker args are going to get passed in here. So we have args dot x0, args dot y0, args dot x1, args dot y1, and then args dot width, and that takes care of those. Args dot height, args dot start row. Okay, these are the remaining. So start row is an integer. I don't know what that should be, so we'll say to do here. And then We have num rows. Same thing. To do. Max iterations would be args.max iterations. And then args. Do I have to dereference? I do have to dereference. That's why I was complaining. So we're going to correct that with that. Args, max iterations, and output. Yeah. And then thread ID and num threads we don't need. Okay, so we got to figure out what we're going to do here. I guess that doesn't like, yeah, okay, let's do that. I don't like that it formatted it that way, but oh well. So if we look at Mandelbrot serial CPP, we'll just go to the, yeah, here it is. So it's given a lot of stuff here. I want to find my main. Okay. Alright, there's going to be a lot of code here to read. I was hoping not have to read everything. Mandelbrot serial. Computer image visualizing Mandelbrot set. The resulting array contains the number of iterations required before the complex number corresponds to a pixel could be rejected from the set. XY describes the complex coordinates mapping to the image viewport. Width, height describe the size of the output image. Start row, total rows describe how much of the image to compute. So these are iterated on here. So start row plus total. So total row is only used to compute the end row. So really you could have done like start and end, but they did start and length basically. And then once you go end, yeah. So they compute I and J. So J is the row, I is the column. And then they do some math, which is this Mandel. Mandel is the test to see if that value is, or how many iterations it take to test whether that value is in the set or not. At least that's my guess here from what it's doing. Okay, so we need to figure out start row and total rows. So let's go back to Mandelbrot thread. So this thing is not given that at all. We say Mandelbrot threads. And then we spin up a number of threads. Each one of these we set wait a minute, are we sharing args here? No, there's an array here. Array sub I, okay. Does x0 ever change? I don't think so. Doesn't look like it ever changes. So y0 probably doesn't change. x1. That's weird. The width and height doesn't change. Width, height, max iterations, num threads, and output. So all of these are, the only thing that changes is thread ID. Interesting. So we're just given each thread the entire set of arguments instead of computing what arguments that thread should be operating on, which would have probably been a better tactic. Given that args here is an array, it seems like they might have wanted to do that. per thread arguments here, the code below copies the same arguments for each thread. Yeah. Okay. So that's all they got to do here. So what do we want to do here? So you can divide it by columns or by rows or by columns and by rows. Usually I try to do the simplest thing first and then get more complex from there. So let's just do rows. I think rows would be a nice way of going about it because each thread can scan linearly by row, and because we are row or ordered in memory, our access will be sequential instead of column ordered where we're jumping around different cache lines. So what we need to do is take the num threads here. So we'll say rows per thread is going to equal to num threads divided by, or no, sorry, num rows. How do we know how many rows we got? I guess the float? No, the height would be the number of rows. So we'll say height divided by num threads. And we'll just say auto here. Okay, height divided by num threads will give us rows per thread. He's using camel case here, so I'll stick with that convention. Rows per thread. So our width is going to be the same, but our height is going to be height will be rows per thread times I plus 1? No. Let's visualize this. So the first iteration, say the rows per thread is 10. So we want to say 10 here. Next one will be 20. And say our total height was like 35. We'll say 35. So height is equal to 35. Oops. Then we'll do a 30. And then this last one will be, our height would be just rows per thread. Yeah. Width is the same, height is rows per thread, but we have to adjust our X and Y value, or I guess in this case it would just be the Y values. Reorder them like that. I think that's what we want to do. So we have our width, we have our height. I wonder why X, Y, X1 and Y1 are floats. So I think I gotta go back to the Mandelbrot serial and actually look at this again. Like, why are they using floats here for dx and dy? So they take x1, which are floats, minus x0 divided by width. I might just draw this out real quick. Scala draw. leave that there. I'm not sure what that is. So say we have this is our viewport. Mandelbrot serial. Compute an image visualizing the Mandelbrot set. The resulting array contains a number of iterations. Did I already read this? X and Y describe the complex coordinate mapping into the image viewport. So it's completely divorced from like the pixel values. Right? Start row and total rows. How is this thing called again? Let's go back into our main serial. So start row is 0 and number of rows is height. So width and height, start row and num rows are the things that control the access into the output array. And then these values are strictly for computing those values. They're not coordinates into the viewport at all. They're what the viewport's looking at, not where in the viewport we're computing. So let's go back to thread. I think I need to modify the args here, even though that didn't say that I'd have to. So width is going to be the same. I guess we can put these back like that. Height. Basically, we need to offset. Yeah. Implement the body of the worker thread here. Each thread should make a call to Mandelbrot serial to compute the part of the output image. For example, in a program that uses 2 threads, thread 0 could compute the top half of the image, and thread 1 could compute the bottom half. So they expect you to do the splitting inside here, but here they're spawning the thread with args, num threads. I'd expect the splitting of the work to be done outside of here. That means that we need to also add start rows and num rows. So let's add those. So height start, we'll say int start row, and int num rows. Yeah, total, they call it total rows? Start row with total rows. Why does it say num rows here? Oh, because they renamed it here. Num rows, okay. Well, that's a bit weird. This needs to be semicolons. Okay, here we're gonna say it's gonna be args. Oops. Args. This will be start row. Args. Num rows. I don't like it when like the for declaration names don't match the actual implementation and argument names. That's kind of annoying. Okay, so now we have to compute. So our height changed to rows per thread. So here we're gonna have start row is going to be rows per thread times I, basically. And then our num not num threads, num rows will be our height, right? I'm kind of confused why they need num rows and height. What the number of rows that you're outputting is the same as the height, right? Let's see how they're using it here. So they call it total rows here. Start row plus total rows and num rows. Height here is used just to compute dy. So height is only height and width. If we look here, width is used for iteration, but height is only, so they're kind of giving the same information twice here. Height and total and num rows or total rows are actually the same value, it seems. And height is used for computing dy, whereas total rows is used to compute the end. So I think there's a little bit of duplication there. I don't really like this prototype, to be honest. How much of the image to compute the size of the output image. Yeah, I don't like this prototype. I'm not a fan of this. Okay, well, let's go back here. We'll just say that is equal to that. No number named star row, start row. And then the only other thing is that we need to handle the remainder. So basically we need to add that on to the end, the last one. So that would be here. In fact, I'm just going to read the height here just to make sure I'm only doing that once here. And let's add it to do. This seems like duplicate info. So here we can say, actually, no, I'll leave that be the way it is. Down here we can say if I is equal to num threads minus 1, then we're on the last iteration, in which case we need to update these values. So we'll go down. Width stays the same. It's rows per thread is going to go higher. So these three values are going to go higher. So we're going to copy them here. Rows per thread plus the remainder. So we'll just say auto remainder is equal to, we'll compute that out here. So hey, remainders is equal to height mod num threads. Okay, and then down here we can say if remainder and I is equal to that, then we do this. Remainder and start row, that remains the same. We don't have to change that. It's basically just these two things we need to change. And since those are just, this is the same statement as before, and then this one is just adding the remainder. So maybe pull this out. So this we can do away with, and then this becomes a wrapper around the height. Kind of. I think what we do is here, oops, pull this up top and say, hey, if the remainder and then we say maybe here, like that. That would work. It's not really beautiful code, but I think that works. So we just say, hey, rows per thread. This we can do a plus equals here and just add the remainder there. So we say if there is a remainder and it's the last thread, we're just going to add it on to the height, which will then get assigned in here. Okay. That seems like it should work. Let's go ahead and do a make. And then we need to do a run, which will be... I don't know how to do this. How did I do it last time? Mandelbrot view 2. Okay. We'll do view 1 because I think that's simpler. It's the whole image. Okay, we did Mandelbrot serial. And then we wrote the image thread. And we said, hey, the 1th row, 142nd column, we expected a 0 and we got a 1. So it doesn't match a serial output, so we got a bug. But I want to display what it would have been. Display Mandelbrot thread ppm. So it looks like it got squashed, which is interesting. Versus the serial. Let's do that. Move that over here, and then we'll do the same thing with serial. So you can see I did generate the whole thing, but it's almost like it got squashed in half. Like if I did a squash that way, these would line up. So it's computing the whole set, which is good. But something got messed up with the viewport. I think our height got doubled somehow. Which is bizarre. Because it's computing all this stuff down here. So that means that the Y value got doubled, I think. Well, let's go ahead and log some stuff. I think I'm gonna have to pull open the main and do some reading there. All right. Here we go. So this is where we start running the threaded version. We declare our outputs here. This is all just parsing command line stuff. We initialize x0 to be -2, x1 to be 1. So it's from -2 to 1. And then y0 is going to be -1 up to 1. So it's going from the bottom left up to upper right. That's the coordinate view. All right, and then we say min serial is 1e30, run the serial implementation, run the code 3 times and take the minimum to get a good estimate. Minimum, okay. Oh, the minimum of the runtime. That's what's being computed here. And this is a very large power. 1 to the power of 30. 1 to times the natural number to I don't know, how do you compute that? We'll just say in C++, what does 1e30 represent? I think it's e to the power of 30. No, 1 times 10 to the power of 30. Why is it an e then? I forget. Let's see here. E means times 10 to the power of. Okay, so we say here, why do they use e? That seems to be confusing with the natural log number e. Exponent, not Euler's number. That makes sense. So 1 times 10 to the e. It also doesn't make sense that they didn't do binary. Like why go 10 to the e instead of 2? Sorry, why do 10 to the 30 instead of doing 2 to the 30? Or 2 to the whatever. Anyways. Alright, so we do memset 0. So width and height is going to be our size. Star thing, then we call. I don't think x0 ever changes, right? Let's go back up here. Oh, there's some scale and shift stuff going on, but if you look here, x0, that's just parsing. So min serial x0 never changes. And I guess it didn't change in our output for threads. It was y0 that changed. But I don't see it being mutated here. Run threaded version, so do the same thing here. Mandelbrot thread. Oh, it gets run multiple times. That shouldn't be a problem though. Each one completes by the time the next one runs, and because the threads wait, I'm pretty sure they wait. What is this scale and shift thing? Is that in the parsing? Yeah, it's in the parsing. Usage, same thing. Verify results. That's just going over, making sure everything matches. Okay. Are these identical? No. They get a num threads. 0, y0, x0, y0, x1, y1. Width, height, max iterations. But I'm giving it max iterations output. There is no start row or end or num rows. Why would you change the prototype for those two? On the serial, I would think that they would be present in the threaded version, not. I would think they would not be present in either version. Because that's indicating that you're gonna change them, right? Per invocation. So in here, start row is 0 and num rows is always height. But then thread, why don't you do the same thing? Doesn't make sense. Like if you're not going to use them in Mandelbrot serial, it's just very inconsistent. Alright, let's go to the threaded version then. And see if we're monkeying with anything here. So x, y, x, y, x, y, x, y. It would be y, y0, right? I think y0 gets messed up. Okay, we're passing it incorrectly there. Let's just print them out here. Printf, we'll just say x0, we'll say like this maybe? %d, %d, %d. These are floats though. F. Oops. Let's see here. X0, Y0 to X1, Y1. And we'll just say here, it's going to be called from Mandelbrot thread. And I got my new line. Cool. Make. Let's go and rerun it. This guy. So -2, -1 to 1, 1. So the ranges are correct. Let's do the same thing here. Thread start. This will be worker thread start. And then this will just be args. -2, -1, 1, 1. That looks correct to me. Okay. So we're going to say all those XY coordinates are correct. And then we're going to go into here and we're going to say, hey, let's try looking at these other values. So this will be int %d width by height, args width, args height, all right, 1600 by 600. Width and height, start row, and num rows. Down here, I'm going to say the number of threads. It's the only thing that's really important to report here. %d. Num threads. Two. So it's 1600 by 600. So we got 0 to 600, and then the last one was 600 to 600. So you got to fix that. That's wrong. What are we reporting here again? Start row and number row. Should probably just do it like start and num. So I think these values are just completely messed up. So our height was 600. So it should be 1 to 300, 301 to 6, something like that. Or 0 to 299, 300 to 600 or something like that. But it's not, because our height, this is where we messed up. We were using height instead of rows per thread, I think. I think that was the problem here. So rows per thread. So here we can say printf rows per thread %d new line rows per thread remainder okay, and then inside here so height will be the rows per thread. I think our rows per thread are just being miscalculated. Say height here. Okay. Make. All right, so our height is, how did our height get 1200? That seems wrong. Let's go over to our main and see where we're calling this and why the height is doubled. Printf %d why is it 1200? I don't see it getting modified here. Okay. Now I'm really confused. So 1200 is correct. 1600 by 1200, okay. So our height is correct going in here. For some reason I thought it was giving us a different value there. This thing. Okay. So we have to, well, first we have to +1, right? Or we can say it's not, oh, it's number instead of the end. Yes, it's num. So that's correct. That actually is correct. So it's working on 0 to 600 and then 600 to 1200. It might not get the last one though. Because if we start at 0, 0 is the first one it does. That means that 599, and then we start at 600 and we go to that, but we have an extra one at the end that we have to take care of. Is that the case? Do we start at 0? I think that's the case. Because our output here is width times height times the int. Yeah, so we don't need that last one. Okay, so that's fine. Okay, so I have no idea why this is doing what it's doing. Let's go back in here. Let's look at the output again. So our height, our rows per thread, remainder is 0. Looks good. Yeah. To be honest, I don't understand what's going on here. Let's do the display again of the thread. So it looks like it's computing every other row. Like if I full screen this, it's not very good. Let's go back over here. Maybe I can figure out a better way of viewing this. View original size. Resize. Yeah, so it's definitely 1600 by 1200. So it's showing, it's basically, it's computing all this stuff down here. I don't understand. I just don't understand. It seems like the it seems like the y0 value is set to like -3 or something. View original size. Yeah, it looks like it like doubled the, because those pixels don't even exist down here. It must be something when I'm calling this. Maybe the prototypes are different. Let's jump into here. Well, let's jump into the actual serial code that's linking against. Grab this prototype, go back over to here, and make sure it's correct, because this for declaration here might be throwing me off. So it's x0, y0, x1, y1, args width, height, start row. This is where it's different. It says num rows versus total rows, max iterations, and output. Seems correct. Let's go into here and we'll print out that stuff here. So here we'll just print out printf out inside, let's say serial, %f, and then %f, x0, y0, x1, y1. Okay. And then we have to pound include that. We'll do it up here. Pound include standard IO to H. Okay, make jobs program. Okay, good. Let's do this. -2, 1, 1, 1. And then we'll do a width height here. And we'll do a width %d x %d. Oops. These are all conserved. They should all be the same value, right? If I grep, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It does 5? So I should get 15 out. Grep for serial. Sorry. Grep for that. Oh. It does make sense for it to be like that. But this might be where the height is like... Yeah, I think my height needs to be 1200. I think that's the problem there. So let's go back over to thread, height. This height actually needs to be the original height. Like we don't change that value. But this value gets changed. Num per rows. Num rows is rows per thread. We'll say num rows plus remainder. There we go. I think that'll work. Hey, looks like it worked. So let me go and delete a bunch of stuff, the printfs I had. So the idea is that like the output image isn't changing. So the height is used to compute that dy value, but it has nothing to do with the output. So I should change the output thing, which is the num rows, but not change the height of the image. That's just something that's conserved. Again, I think I understand now what's going on here a little bit better, but I think their API design is leading me to wonder about some of these things. Okay. So let's go ahead and delete some of these printfs. So that was me. That was me, obviously. That one as well. That one is just an fprintf that already existed there. Let's go to serial. That was me. Delete all that. And then if we go to main. I think all these existed before me. Let's go back here and we can delete this pound include now. Okay. Make, let's go ahead and rerun it. Cool. And I got a 1.9x speed up from 2 threads. It took me entirely way too long to figure out that argument, the height argument, was wrong. Like, if I was designing an API, it's like the height would be like the area that the thing is working on, not the total image that is available in memory. Because here's the deal. When you're creating code that you want to be kind of, you want it to be ignorant of like the memory space that it doesn't need to know about. And by saying the height is 1200 pixels, I understand now that that's not influencing the output at all. But it almost seems like it should, because that height value only has an impact on the mathematics of computing whether a point is a member of the Mandelbrot set. It doesn't have anything to do with the output memory data. And because it's an integer value, it almost makes it seem like it should be. It's like you're saying the height of the image. It almost seems like it should be that something that has to deal with memory, the output image. Otherwise, like, why not just use a float like you did for the x, y values? Because when the x, y values are floats, it's very clear that, okay, this is being used to compute the value. It's not being used to index into an array. Whereas a integer value makes it seem like it is used to index into an array. So if we look over here, let's go back to, was it Mandelbrot? We'll do serial. Yeah, this thing here. This Mandel here, I don't really care about that. That's just computing the whether a point is in the Mandelbrot set. But here we're saying, here's the real part, here's the imaginary part, here's the amount of iterations, the max amount of iterations that we want to do on it. That's very clear. But here, look at this. So width, the reason why height became an integer is because they confused width with two purposes. One of them was to compute the value of dx, which is the math, the float math. The other is the number of iterations that we're doing per row. So width is used to compute an index. It's used to compute the number of iterations that we're doing, and it's being used to compute the dimensions. And then here, height is being used to compute, width has two purposes, or two different types of purposes. One deals with the output image, so computing the number of pixels in a row and computing the index into that row, or index into the output, I should say. So it's with in this situation has a very output oriented use, and it should be an integer. But then it's used to compute dx, which has nothing to do with the output. It has to do with the actual value that's being generated, the mathematics of the value that's being stored in the output. So width has this dual role. Height does not have that dual role. Height has only one role, which is the mathematics to compute the value of that pixel. It has nothing to do with the actual number of rows. They split that out as a separate value. So the fact that height is an integer is only an after effect of the fact that width was an integer, and then width has dual purposes both in the mathematics and the dimension of the output. And so that's why I'm a little bit confused. I think if I were to approach this, I would completely separate these use cases, because you have height separated. So why is width not separated? And if that's the case, it's very clear these are two different separate domains. So I think what I would do is say width and height should be floats, and width should not be used to iterate here. There should be another value. Or if you're going to try to put them together, no, I think I would just separate them apart, because trying to put them together is not going to work either. So yeah, I would completely separate these things. And then very clearly specify what they're used for. And I think they did do it here, kind of. Width and height describe the size of the output image. Well, is that the size of the output image in its totality, or just the output image that is being worked on by the serial routine? Because in a parallel structure, if you have like multiple threads working on different areas of memory, they never need to know about the other areas of memory that are available. So yeah, in this situation they kind of do. They know that everything is this width size, and they know that there's a ultimate height to it that they're working within, and that start row is an offset into that height. So each thread kind of knows about, or can figure out where they're at in the array, which stylistically I prefer each thread to kind of just be ignorant, just focus on its little subsection and not really know about the larger structure of the array, the output array. So yeah, I think I just have like some issues around this, the prototype here, the variable, the arguments, how they're being used with dual purposes. It's not very clear. I think that's what threw me off here. Anyways, that's enough going into that. Let's close this out. I don't need to use that anymore. So let's continue reading in this assignment here. I forget where I left off here. Your job is to parallelize computation of the image using standard thread. Start code that spawns one additional thread is provided in a function mandelbrot thread located in mandelbrot thread CP. In this function, the main application thread creates another additional thread using the constructor. It waits for this thread to complete by calling join on the thread object. Currently, the launch thread does not do any computation. It returns immediately. You should add code to worker thread start function to accomplish this task. You will not need to make use of any other standard thread API calls in this assignment. What you need to do, modify the starter code to parallelize the mandelbrot generation using two processors, specifically compute the top half of the image in thread 0 and the bottom half in the thread 1. This type of problem decomposition is referred to as spatial decomposition. It's different spatial regions of the image are computed by different processors. Extend your code to use 2, 3, 4, 5, 6, and 8 threads. Partitioning the image generation work accordingly. Threads should get blocks of the image. Note that processor only has 4 cores, but each core supports 2 hyperthreads, so it can execute a total of 8 threads interleaved on its execution contents. In your write-up, produce a graph of speed. Okay, so there's a write-up. Is that in the written assignment? Let's go up to parallel computing. This thing here, written assignment 1. I don't see it here. These are rather long. Mandel thread. Yeah. So this is not part of the programming assignment. So there is a type of write-up that they want. Let's search for write-up. Okay, hand-in instructions. Handed it so-and-so, the only one hand-in per group is required. Oh, this is a group project? Okay. However, please make sure that you add your partner's name, place it, blah, blah, blah. Okay, so assignment and code. You write up in a file called writeup.pdf. Please make sure both group members' names and subnet IDs are in the document. Assignment code 1, implementation main CPP and program 2 in a file called prob2.cpp. K-means thread, program 6 called prob6.cpp. For example, because you attempted to write any additional code, for example, because you attempted an extra credit, please tell CAs to look for your extra credit in your write-up. When handed in, all code must be compatible and runnable out of the box on the Myth machines. Okay, resources and notes. Extensive IASPC documentation examples can be found at this location. I've been here before, but I haven't read the documentation. Zooming into different locations of the Mandelbrot site can be quite fascinating. Intel provides a lot of supporting material about AVX2 vector instructions at their documentation there. The Intel Intrinsics Guide is very useful. Let's zoom in here, or zoom out, I should say. So I want AVX 512 float. So these are all the different things that operate on AVX 512 float. I think that's what that means. Let me uncheck that. So this is where the underscore MM is from MMX. And then SE continued on from there. But by the time we get to AVX 512, don't they change some of that? No, it's still MM, but it says MM 512. AMX, I'm not familiar with that. Ooh. Yeah, they got a lot of functionality here. It's kind of insane. All right, that's good to know that exists. Let's do a write-up instead of, let's do a find iname and just search for write-up. Nothing here. So I'm gonna just create a write-up.md. We'll say assignment 1 write-up. Here we'll say problem 1. Okay. Are there args for this that I can run different threads? Let's do cd prog1. And we'll run our Mandelbrot help. And we do indeed have a threads, so we'll do 1. Make sure that works. Yep. 2, 3, 4, 5, 6, 7. So we keep on improving our speed here. 19x, 16. Oh no, 119x, 163, 248, 316, 8, 9, 10, 11, oops, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. What is the best open source format for storing data points for analysis with something like pandas or I don't know. Yeah, we'll say pandas. For most serious analytical workloads, CSV for maximum interoperability and simplicity, Apache, Arrow, Feather. Okay, I think I'll just roll with CSV. And what I'll do here is I'll say, hey, can I grep for speed up? There we go. And what we're going to do is we're going to awk out print $1. Does that give me that? Yeah, and then we're going to, before we do that, we'll do a tr on that to that. Oops. To that. There we go. And what we'll do here is we'll say for n in 0 to 64, do echo $n done, and we'll just comment that out. There you go. So I just want to make sure it prints everything out. Now we're going to say do echo n, but we're going to say no new line. So I think it's echo, what is it? Yeah, n. Mandelbrot $n. And then in here we could say comma. And I really don't want to go to 0. I don't think having 0 threads would be helpful. Cool, that looks correct for me. Okay. Oh, I don't like that X at the end. So maybe I can translate that off. Yeah, let's do a translate here. TRX, like that. There we go. So this is going to be our command, and I want to save this. So we'll just say generate data, thread data, sh. We'll fix this up a little bit, fix that. Grep tr there we go. chmod plus x that, and just run it. Oh, what? Oh, I messed up this command. That's going to just output to the terminal, so I think what I'll do is say, hey, you're actually going to a new file and call it, what is this, thread data.csv, and we just bam, and then jump over to threads, tail, thread data. Okay, so I extended it to 64 since I have 32 cores. I think I have 32 cores. How many cores do I have here? CPU info, sorry, proc, CPU info, grep for core ID. I think it's called core ID. So I just have 32. Oh, interesting. So I think max allowed threads is 32. I think that is the program. Max. Actually, rip grep for max allowed. Yeah, Mandelbrot thread CPP max allowed threads was just hard coded here. Okay. Let's go ahead and edit that. Just turn it to 64 here. And then we'll rerun this. Sorry, guys, we're gonna make, rerun this, and then rerun our tail. So in principle, I should only be running up to, so he did 8 threads, which is 2 times the number of cores. So if I were to do that, I would be doing 32 threads, which is 2 times the number of cores I have on my machine. But I also want to go even double that to see the diminishing returns when you're saturating all cores, but now you have a bunch of threads waiting to do work. You're not getting any benefit. So that's my hypothesis, is that we'll see benefit up to 32, and then anything after 32, we won't see any benefit. In fact, we'll see the opposite. So I think 33 what? Now we're starting to, oh, just keep on going up, 15. Starting to level off. Okay. Let's go and plot that. Okay, what are we doing here? I want to ask AI. I have a CSV of 2 values, and we'll say num threads and what is this going to be? Runtime. How do I easily plot this. To see it on a line chart. Seems like Python is gonna be the best way. So I'll go back here and I'll do Python m vm dot vm and then do dot vm slash bin activate. Sorry, dot that. And then I'll do this. Then pip freeze into requirements. .txt. Okay, just want to make sure I spelled that right. And then we're gonna write our script here, have ChatGPT write it for us. Back in here, we'll just say vim plot thread data dot py, and then here we're gonna read thread data. Call this num threads runtime. Actually, we'll stick with the camel case because that's what the C++ code was using. All right, so num threads runtime. Number of threads, runtime versus thread, grid true show. Okay. So this is using something called PLT, which is in matplotlib. Okay, cool. Let's go ahead and I need to fix my script. We'll just say, hey, this is gonna be thread data 2, and first we need to echo out echo num threads and runtime. Speed up. We'll call it speed up. So we got to echo that out, and this whole thing needs to be in a subshell now. Boom. That we capture here and redirect its output. Okay, so let me fix this. We'll do chmod on plot. Sorry, plus x plot that vim that. I need to go up here and say hash bang. Oops. User bin env python. Okay, and then if I rerun my generate thread data shell script, I'll let it run here for a second, then I'll kill it, and then this thread data 2.csv. Okay, num threads speed up, then thread data.csv. That'll get num threads and speed up. Bam. Okay, and then we rm thread data 2 and fix our generate script to not have that 2. Okay, so now everything's good there. And then this guy is going to be speed up. Runtime speed up. Make. And then here we're gonna say plot. Okay. wonder if I can output this somewhere. Can I? Yeah. I don't want to use GNU plot. I like matplotlib. I'm going to stick with it. So with matplotlib example, first, how do you save the plot to a file? Okay, so we killed that. Vim into that. So we did grid true, and then it's a plot save figure to runtime plot DPI 300 box inches tight. All right, plot. So that shows it, and then we also get this nice file that we can then open later called runtime plot PNG. I don't like that. I like the other one. Let's do plot. Maybe drop this and rerun it, because that's what it looks like here. Open. Sorry, not that. Open runtime plot. I don't like the way that looks. Plot thread data. How about we just do that then? Plot thread data. I like this graph here. And then open runtime plot. Still garbage. Okay. I like the way the plot shows up with plt.show, but the saved save fig image doesn't match it. What gives? I don't think it's gonna happen. Tight layout. Maybe if we try that. Plot. Plot. Has no effect on this. DPI 300. Okay, open. The problem is that the line thickness is higher and the points on the graph are larger circles. Everything appears larger. think it's fine. Okay, what does it say here? Partitioning the image generation work accordingly. Threads should get blocks of images. Note that the processor has only 4 cores. Each core supports 2 hyperthreads, so it can execute a total of 8 threads interleaved on its execution contents. In your write-up, produce a graph for speed up compared to the reference sequential implementation. As a function of the number of threads for view 1, is speed up linear in the number of threads used? In your write-up, hypothesize why this is or is not the case. You may also wish to produce a graph of view 2 to help you come up with a good answer. Hint, take careful look at the 3-thread data point. Well, I'm not going to be able to use that. Let's go back to generate thread data. This will be thread data view 1. And then we'll do thread data view 2. And then this just needs to get view 2. Oops, sorry. It needs to go over here. Okay. I think it's view space 2, right? What is the arg? View dash view 2. So I'm not in go. Plan 9. Okay, so that gives both of those, and I'll just comment this one out for now. Actually, fuck it. I can just run it on all of them. We'll just do rm thread data, and then plot thread data. It's thread data. Well, let's just get it running here. Jump over to prog1, generate thread data. So this will be thread data view 1. Data frame 1, 2, plot df 1, df 2, So this had a pretty consistent linear growth. Um, Up to about 40 threads. Same thing here. This one's a little bit more volatile though. And then after 40 threads, it kind of just goes chaotic. So if I cat out my CPU info again here and do a word count L, so it's 32 threads, 16 cores. So I can embed these. I think I do bang, and then I do it like this, I think that's how I do it. Or is it like this? I think it's like this. No, we'll try it like this for now. And this is going to be ASST1 slash okay. Problem one. Let's do grip right up. D. Pac-Man search for grip. Nope. Usually I stick this in a virtual env. Okay, whatever. I don't have the virtual env activated, do I? Python, or say which? Python? Cat requirements. But here I do which Python. It's my virtual env. So I think what I'll do here is say sudo pip install. Can I just do pip install here? Grip pip3 install. Okay, I'll just do it in the virtual env. ///vm bin activate, and then we'll do our pip install grip here, and then I'll do grip write up. So that's not showing up. Yeah, it is the right syntax. But I don't have any alt text. Oh, it's because it's under here. Got my URL wrong. There we go. So I observe a linear relationship between the number of threads used to compute the set on the speed up and runtime used to compute needed, I should say, needed to compute is set up to about 40 threads. The system I am running this on has 32, or say 16 cores and 32 threads. This was true for both views, but view 2 was more consistent. I should say that after that, yeah. Let's pull this out. In both views, the runtimes got volatile. Is that how you spell that? Volatile? I think that's how you spell it. No, volatile. Got volatile. This is almost certainly due to the cores being saturated with work. So using more threads does not extract more parallelism. Three thread data point. It did decline there, but not here. The assignment mentions the 3-thread data point, and on view 1 I do indeed show I see a data point that is less performant than 2 threads. My hypothesis for this is that when the whole set is divided into 3, the top and bottom parts of the set have many data points that are easily determined to be not in the set. However, the middle section has has quite a lot of data points that take time to compute the maximum time to compute their membership in the set. As a result, most of the time computing this set is in this one section, versus with a two threads where that work is shared. I'll just say shared. That's my guess. Okay. I feel like that's a pretty good write-up. To confirm this appropriate hypothesis, measure the amount of time each thread requires to complete its work by inserting timing code at the beginning and end of the worker's thread start. How does your measurements explain the speed up graph you previously created? Okay, let's go and do that real quick. Thread. This guy here. Minimize that. In fact, I think I'll do a G on this and throw that up there and bring that over there. Cool. Alright, so yeah, this can be localhost. There we go. Oh. Come over here. I would like to get this done, and then I might break here. How long have I been streaming for? 2 hours? I might break here after this first problem. After having the write-up done. He said add timing information to worker thread start. So we'll do a printf here. He did have timing around main. So we'll just do the same timing stuff, right? Here. Start time, end time. And then subtraction. So we'll go up here. Start time. End time. Oops. And we'll do a printf here. Okay. This will be printf time to run thread. Do I have a thread ID here? I think I do. In args, right? Did I pass that in? Yeah. So %f maybe? How did they compute? So this would be args thread ID. If I go over to main, so they do this end time, which is double. And then they're saying that's an amount in milliseconds. Okay, times 1,000 would be a number of milliseconds. Okay. So we go here. Times 1,000, but the 1,000 means happen. The multiplication has to happen after the subtraction. And this will be ms. Min thread. Oh, I don't know why I'm doing that. Thank you. Oops. Mandelbrot threads 3 view 1 sure, let's do that. I need to do my thing here. Modify the mapping of work to threads to achieve modify mapping of work to threads to improve speed up to about 7 to 8x on both views. Well, I already got a improvement of upwards of 15x, bro. If you're above 7x, that's fine, don't sweat it. You may not use any synchronization between threads in your solution. We are expecting you to come up with a single work decomposition policy. A single work decomposition policy that will work well for all thread counts. Hard coding a solution specific to each configuration is not allowed. Hint, there is a very simple static assignment that will achieve this goal, and no communication synchronization among threads is necessary. In your write-up, describe your approach to parallelization and report the final 8-thread speedup obtained. To be honest, I don't really have any ideas here. My ideas required synchronization. Whew. I guess if we wanted to keep it static, say we have 3 threads, then we would do mod 3. Instead of doing the first chunk, we would do every 3rd row. We'll say the problem asks for an alternative static work assignment. However, that we'll say here, or that would require between the threads to coordinate which is that supposed to coordinate? Yeah. Thread is working on which unit of work. However, the static work assignment with no synchronization. An alternative might be, instead of computing a contiguous block, in each thread, have each thread compute individual rows mod the number of threads. With the this might provide a more fair distribution of work, since work between the threads given rows, given the hypothesis that rows near each other have similar require amounts of time to compute. Okay, let's go ahead and implement that. It's going to be a big change. Status git add p. Yes. Yes. Okay. Thread. Okay, maybe we can add this in an arg, maybe? Hmm. Okay. So how we might do this is, I guess up here, we're handing off to Mandelbrot serial. So at this location, our thread already has, okay. Oh, we get thread ID as I. Okay, that's why they wanted to not send these down as args. So I think what I'll do is I'll pull those out. And I'll put them over here for now. We'll delete them out of here. Okay. Oh, and I have to compute rows per thread too. And num threads. Num threads. So num threads does come through. So we have that as an arg. So we can say args num threads and args height. Remainder args height and args. I'm going to reinvent what I did already, but doing all the math here. So this will be rows per threads times I, which will say auto I is going to be equal to args thread ID. I think that's, yeah. All right. And this will just be auto num rows. And then if remainder and I is equal to num threads minus 1, then we're going to have to add that on to num rows here. Num threads will be args, num threads. Alright, I just want to keep that for posterity. Alright. We'll say row is less than height. Row is equal to thread ID. We'll say I. Let's just delete this thing and say I. Yeah, you're gonna be args thread ID. Something here. So I do like that. So args thread ID. We'll say auto row. As long as row is less than height. So the height, say we had 10. And we have 2, or say 3. That'd be 0, 1, 2. And then each one of these, we're going to say row plus equals the mod, which I'll do the mod out here, which is, where's the mod? This thing here, remainder. That's not it. Rows per thread. So this would be rows per thread. I don't think I need the remainder on this. I think I'll catch that. Because if we had an odd spaced thing, we're just going to keep on adding until, yeah, I think that would be fine. Okay, so that means that start row is going to be the start row is going to be row, and number of rows is going to be 1. Less than args height. Oh, maybe I do our cycle timer. Yeah, this guy needs to be up here. Well, we'll save that, and then we'll do this here. Else. We'll do an else. Do the same thing here. Okay. It isn't rows per thread. It is... Is it? It's how many threads. I don't think I have to do this. I think I need to say plus equal to args num threads. What do I mean start to... Oh, because it's not... okay, I'll do it out here then. Why not? So integer expressions of different signedness, int and unsigned int. So arg's thread ID is an int. So we convert this into, oops, sorry. Arg's height is unsigned. Can we just convert it to an int here? There you go. Yes. Okay. How do I run this again? I run the generate thread data. Oops, sorry. Generate thread data. Guess we'll see how. Oops. Huh. Got up to 23. That's some interesting results. I wonder if it's correct. I didn't check for correctness. Yeah, I'll go ahead and kill it. We should run Mandelbrot v2. Make sure that root image file u1. Okay. I'm gonna go ahead and rerun this then. Do that. So we got up to 20 something, and then in our write up here, we didn't see anywhere near that. So we definitely have better performance just from a better work assignment policy. And very quickly hit diminishing returns with threads. Regress. Let that run for a second here. Check in on something else. Alrighty, sorry about that. Got distracted while I was waiting for that thing to run. Alright, so we got our policy 2. So I'm going to modify my plot here to also do policy 2 here, which means I should turn this into a new line delimited list. Copy these over here, and underscore policy 2 there. And I'm not going to show. I'm just going to save the figure. Get status, get add p. So we'll fix that and that, and that. And we'll also get add thread data star status. There we go. Alright, let's go ahead and run plot thread data. We should get 2 new plots. Get status. Oh, and we modified view2 CSV plot. Well, if you go here, I'm going to close out of that. View2 thread data view2 CSV PNG. That would be this one here. If I refresh that, I think it's about the same. Oh, interesting. This thing has 2 data sets now. Interesting. I bet you this one has 3. So let's do open that. Yeah. So we're just adding data sets. So if I run my plot thread data pie, what I need to do is isolate these plots. I'm gonna have AI do that. Say isolate these plots so the data is segmented by plot. Boom, boom, boom. I think you need to instantiate something instead of using this global PLT. Yeah. Exactly. So let's go ahead and paste that here. Oops. Didn't copy it. Okay. So this is a figure and an X. We then call our plot the same way. Our labels same, grid, layout, save fig, and then we close it. Okay, looks good to me. Cool. Get add to the plot thread, and then we'll rerun it. Oh, df now is changed. Okay, did I mess something up there? Oh, I didn't grab my df. My bad. Okay. Good status. Okay, now we just have 2 millions. Good. If I refresh this, it should be back to business as usual. Okay, so I wanted to open up thread data view policy 2. View 1 policy 2? Yeah, policy 2. Sorry, wrong one. PNG. There we go. So you got very high performance at a very low thread count, which is nice. Oops. Let's create another one here. Messed that up, sorry, my bad. S. There we go. Open thread data view 2 policy 2 .png. So that's that. Okay, let's go ahead and add them to the write up. So grab them here, put them down here. And this is just going to be policy 2. Okay, so what we see here is that basically we get performance improvement up to maybe our maximum hyperthread count. And then it's all overhead from there. That's a much better graph, to be honest. Yeah, better performance. We're seeing performance all the way up to the number of threads that we get. Okay. Individual rows. Okay. I think I'm going to add this to here. And rerun that. Sorry, I need a dot slash dot VM dot bin activate. Do that, and then I can rerun this. And that will make these plots clearer. Okay. We see not only do we get a fair amount of additional speed up in the runtime, but we also see that at around 32 threads, we reach full saturation of all available hardware threads, which is exactly what the number of functions, which makes given we have 32 hyper on this machine means we are achieving great. That's really cool. All right, let's go back here. Now running proof of code with 16 threads performs much greater than when running with 8 threads or not. Okay, that is that first problem. So I'm just going to commit that. Git add p now. Yes. Yes. Git status. The PNGs I'm cool with. Yep. Let's do add all. Git status. Git CI will say complete problem 1. And then git remote v. So I need to update my remotes here. I need to clone this thing. Or fork it, I should say. Sure. And then git oh, this is submodule, so vim.get remotes, no config conf. Yeah, submodule, here you go. And we'll do git at github.com colon cipher0 dev dot git. There's no git here. So git status vim.git. There should be something else here. Modules? Well, that's a different thing. I need to be able to push that. So rip grep for, or git diff rip grep for Stanford CS 149. And A, I think. think. Man RG hidden. There we go. So get modules. There we go. Vim get modules config, and then here this needs to be get at cipher 0 dev .get. There we go. And then is there anywhere else I need to update? I think that's just reflog stuff. That's fine. Okay, so get status. We see it in here. Get status, get push. All right. Push. Hey. We look here now. Should have her commit. Yep. Can I view this write up as a rich diff? Yeah. Cool. All right. Now we go back here. Get at all, get DC. Looks good. Get CIM. Let's say bump. Assignment 1. Oops. I knew that looked weird. Assignment 1. There you go. This one. And then we have that. And if we look at right up that MD, got our nice little charts and everything. Cool. All right, well, I'll leave that running there. I'm gonna take a break here though. I need to get some dinner and do my dinner, post-dinner cardio. Hey, what's up? Is this live? It is live. I'm really slow at responding to chat though, so unless I catch something, it might not show up. All right. I'm gonna hop off here then. Ultra slow, yeah. So I guess I can explain what I was doing here before I hop off. But this is a course that I'm auditing on parallel computing. Let me go back here. Yeah, so this is the repo. The actual course, computing, Stanford, Kayvon. It's this one, CS149. And basically I'm watching the video lectures on stream. They're really good lectures. And then I'm doing the assignments. So the first one that I'm working on here is this repo here. And if we go back over here, I did my little write-up. So the basic idea is that you have this Mandelbrot set, and you want to compute this using multiple threads. And how do you do that in the most efficient way, basically? So the first iteration was to use somewhere up to 42 threads here to get the maximum performance of a 17.5x speed up. And similar results on both of the views of the set. And this is using blocked generation. So you would do like, say you had 42 threads, you divide the image up into 42 blocks, and then each thread would operate on each one of those blocks. And that gave a pretty decent result, but it wasn't the better result. The better result was down here, where instead of doing all the rows in order for a single thread, the thread would do one row and then skip ahead to the next block and do that same numbered row in that block. So if there's 42 blocks, it would do a row from each one of those blocks. And you might think like, well, that doesn't really seem like it would be much better, but the reason why it is better is that Mandelbrot set, the amount of work it takes to compute each pixel of this image is not evenly distributed. Like some pixels are harder to compute than others. And so what you want to do is have a division of labor between all the different threads that is somewhat fair, so that one thread isn't doing a disproportionate amount of the work. So the example that I came to was like the 3-thread situation. The thread in the middle was spending so much time doing like 4 times as much work. And we could see that in the data results here. So you had thread 0 doing 48, thread 2 doing 51, and then thread 1, which is in the middle, was doing like 150, which is, 3 times as much work. So that's not really a fair division of labor. So splitting it up and interleaving the rows allowed me to get up to a 27x speed up, 25 to 27x, and I got that speed up in only 32 threads. And then anything after that, you see diminishing returns because we're fully saturating the CPU cores. So anything after that would be oversubscription of the CPUs. So pretty decent result. Happy with it. I also kind of like theorized a work division strategy that would be a little more complex to implement, that requires some synchronization, but it would be more fair. Whether it would be more performant or not than what we came up with here, I'm not sure. But yeah, that's the type of stuff that I'm going to be working on here moving forward. It's these parallel computing assignments, if that's your cup of tea. But yeah, I'm going to hop off here, grab some dinner, do some cardio, and I'll be back on this evening to poke around on this computer architecture book. Because really I want to get started recording some videos on this book and yeah, explaining some of these more advanced master's level concepts in a simple way that, you know, someone who doesn't have, you know, a huge amount of background can approach and understand. So that'll be this book here. Computer Architecture, a Quantitative Approach. This guy here. Cool. All right, I'm gonna hop off here and I'll be back on probably about an hour or two. All right, later.